This series provides DevOps engineers with an introduction to Docker, Kubernetes, and Octupos with the goal of creating an automated multi-environment deployment process to provide a foundation for DevOps teams looking to deploy containerized applications with the speed and reliability that end users now demand. We'll explore the concepts behind Docker and Kubernetes, configure a development Kubernetes cluster, integrate it with a hosted Octopus instance, and finally deploy a sample application across multiple environments. We'll start by looking at Docker itself, and what we have here is a quote from the Docker website that describes what Docker is. And so the website says that Docker is an open platform for developing, shipping, and running applications. So what's interesting is that every computing device ever created has always had the ability to develop, ship, and run applications. Docker has become popular because it solves many of the problems faced by DevOps teams, most importantly the ability to ship and run applications consistently across platforms. This means the behavior of a containerized application is much the same on a developer's local workstation as a production cluster, which brings a lot of confidence to teams managing the DevOps lifecycle. So this is an image of the DevOps lifecycle, and it shows the various stages that an application will go through as it's being developed and then pushed out to production. And what Docker brings to this lifecycle is a level of consistency through each of these stages. Docker can be installed using the instructions available on the Docker website. There are options available for all major operating systems, including Linux, Windows, and Mac OS. And here we will install Docker on Linux, specifically Ubuntu 2022.04. The first step is to remove any previous versions of Docker that may have been installed, and that can be done by running this command here. I don't have any previous versions installed, so this has actually done nothing for my local setup here. We then need to update the package lists with the sudo apt-get update command. And then once that's completed, we will install some of the prerequisites for Docker with the following command shown here. The GPG key for the third-party Docker repository that holds the code is installed with these commands here. We then set up the third-party repository with this command here. The package list is updated a second time to reflect the new repository that was added. And then finally we install Docker itself with this command. And at this point Docker is now installed, so we can skip over these instructions that detail how to install a particular version of Docker and drop down to this step that verifies that Docker is installed. And what this will do is download the Hello World image, create a temporary container, and the output of the code that's executed in that container is this message here. And that means Docker is installed, so we are ready to go. Windows and Mac OS users will have to install Docker Desktop in order to add Docker to their operating system. The instructions are available under the Docker Desktop item in the left-hand menu. Mac users will download these applications here depending on the chipset that they're using in their Mac, while Windows users will download this executable installer from here. Once Docker is installed, the next step is to install a development Kubernetes cluster, which we'll do in the next section. The final step after installing Docker on Linux is to grant your own user the ability to execute the Docker command line tools without using sudo. So to do that, we need to add a group called Docker, which is done with this command here, and it already exists, so that's fine. And then add your own user as a member of that group. Members of the Docker group are given the permission to run the Docker command line tool without using sudo. And so for this change to take effect, you simply need to log out and log back in. In this section, we'll install a development Kubernetes cluster on our local workstation, and we'll use this cluster to demonstrate Kubernetes throughout the rest of the course. It's worth taking a moment to define what Kubernetes is, though. And here is a quote from the Kubernetes website where Kubernetes is described as a portable, extensible, open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. There's a few keywords in here that are worth delving into. Portable, I think, refers to the fact that Kubernetes really does run almost anywhere. Every major cloud provider has a managed Kubernetes offering, and Kubernetes itself can be used to orchestrate both Linux and Windows containers. Extensible, I think, refers to the large ecosystem that Kubernetes has managed to cultivate around itself. So there is a huge variety of third-party tools and products that integrate closely with Kubernetes, and the extensibility of Kubernetes is very core to the product itself. Open source refers to the way that Kubernetes has been developed as a product, where the source code is available to anyone who wants it and anyone is free to contribute to the project. The declarative configuration is also an interesting aspect of Kubernetes. This refers to the fact that most administration of a Kubernetes cluster is done by describing the desired state of the cluster and allowing the cluster to reconfigure itself to match that desired state. This is different from the more traditional imperative configuration that you'll find in a lot of hosted platforms, where the end user is responsible for executing a series of operations in a particular order in order to achieve the desired outcome. One of the consequences of the extensible nature of Kubernetes is that there is a huge range of projects that allow Kubernetes to be deployed onto a local development machine. Typical production clusters will be fairly large in size, in that they quite often require multiple virtual machines or physical machines in order to host all the nodes. This is obviously hard to emulate on a local developer's PC. But there are a number of projects available that allow a small development cluster to be spun up relatively easily, and one of those projects is called Kind. Kind, which stands for Kubernetes in Docker, is described as a tool for running Kubernetes clusters using Docker container nodes. What this means is that Kind can create a development cluster on a local machine by creating all the infrastructure required for a minimal Kubernetes cluster within Docker itself. It can take a moment to wrap your head around the idea of Kubernetes being hosted in Docker to then orchestrate yet more Docker containers, but in practice it works quite well, and Kind is an excellent choice for creating a local development cluster. You can install Kind across the 3 major operating systems, and here the instructions are provided for installing Kind through the macOS Homebrew or MacPorts package managers, and also the Chocolatey package manager for Windows. Installing Kind on Linux involves downloading it and copying it to a path on your local file system, and that is done by copying these instructions here. The final step involves copying the executable we just downloaded to some path on the file system, and so what we'll do here is copy it to a location that is referenced by the path environment variable, which will allow us to run the Kind executable from any directory that we want. So in this case we will place it in the user local bin directory, and that means we can then run the Kind executable from any directory that we want. Once Kind is installed, we can create a development cluster with the command kind create cluster. Kind will download the image used to create the Kubernetes cluster, write a configuration file used to allow command line tools to interact with the cluster, and finally initiate the cluster itself. The configuration file is written to the .kube directory in the user's home directory. This configuration file is used by a command line tool called kubectl, which will allow us to interact with a Kubernetes cluster. kubectl is defined as a tool that allows you to run commands against Kubernetes clusters. You can use kubectl to deploy applications, inspect and manage cluster resources, and view logs. There's no real clear consensus about how you actually pronounce the name of this command line tool. Some people call it kubectl, kubectl, I've also heard, but for the rest of this course we'll refer to it as kubectl. The Kubernetes website has instructions for installing kubectl on multiple operating systems, including Linux, macOS, and Windows. Generally speaking, the process of installing kubectl involves downloading a binary executable and installing it somewhere on the operating system path. To install the executable on Linux, we'll first download it to the local directory. You can optionally verify the signature of the downloaded binary. And the final step is to install the executable into a directory on the operating system's path. And again, we've used user local bin as the containing directory here. kubectl is then available to be used from any directory in the terminal, and we can now use it to interact with the test cluster created by kind. At this point, we have all the resources we need to start working with Kubernetes. The development cluster created by kind and the kubectl command line tool provide us with all the tools that we need to begin deploying applications and interacting with the cluster. In this section, we'll cover a number of the concepts relating to the Docker and Kubernetes ecosystems. The first concept is a Docker image, and we have a definition here that says an image is a read-only template with instructions for creating a Docker container. The important aspects of this definition are the phrasing with instructions for creating a Docker container. The bulk of the image will be made up of the files that are used to make up the container file system. The Docker images also include a number of instructions such as networking, environment variables, and launch scripts that are used to configure the resulting Docker container created by the image. A container then is defined as a runnable instance of an image. The important thing to take away from this definition is that one image can be used to create many containers. To demonstrate Docker images and containers, we'll download a sample Docker image, build it locally, and then use it to create a Docker container. The sample application we'll be building is called the Octupos underwater app, and it's a fairly simple static website compiled into a Docker image. The source code for the sample application is available on GitHub. The first step is to clone the Git repo, which we can do by copying the repo URL here and running the command git clone and then the address of the repo. We then enter the new directory, and to build a image we will run the command docker build and then the dot command to refer to the current directory, and then we will pass a tag in that defines the name of the resulting images. While this builds, we will look at the Docker file, which includes the instructions used to build the Docker image. The sample application has a very simple Docker file. It references a base image, in this case referencing an image created by the Nginx project, where Nginx is an open source web server. We then have a copy command that copies the source code files for the static website into the image. To use the image to create a container, we use the docker run command. We need to publish some ports to allow us to access the web server running in the Docker container, and that's done with the -p argument. The first port here is the port on the local machine that will be exposed, then a colon, and then the second port is the port exposed by the Docker container. We then pass the name of the image that we built previously. The Docker container then executes the application in the Docker image, and because the port has been published, we can see the web application on localhost 8080. And there's our sample web application running in a Docker container. The image that we just built is saved on my local PC and is not available for use by other developers. To share Docker images, we need to use what's known as a registry. A container registry is a service that stores and distributes container images and related artifacts. DevOps teams will use container registries as a way of sharing images between themselves and between the platforms that eventually host the Docker images and the containers that they execute in. Registries contain many repositories. So a repository is a collection of container images or other artifacts in a registry that have the same name but different tags. This means there is a one-to-many relationship between a registry and a repository, and another one-to-many relationship between a repository and the tagged images that it saves. Tags are often used like versions to indicate new releases of Docker images, although technically tags have very little semantic meaning within a Docker repository. When a tag's not specified, most tools like the Docker command line tooling will assume a tag of latest. Latest frequently refers to the latest deployed version of an image, although this is more of a convention and not an enforced rule. Docker Hub is just one example of a Docker registry, and here we can see the underwater app has been published to the repository called Octupos samples/underwater-app. We can use this registry instead of building the Docker images locally. To do so, we copy the registry name and use a command like docker run, exposing the same ports as we did before, and then pasting the full name of the image found on Docker Hub. Docker will download the image from Docker Hub and then create a container from the image. As before, we can open the web app hosted in the Docker container by opening localhost 8080 in our web browser. We now start looking at the resources and concepts relating to Kubernetes. The first concept we need to cover is that of the Kubernetes object. And so we have a definition here that says Kubernetes objects are persistent entities in the Kubernetes system used to represent the state of your cluster. What's important to take away from this is the idea of persistent entities, which means that Kubernetes is responsible for maintaining a database of the Kubernetes objects that should be created in the Kubernetes cluster. Often Kubernetes objects are represented as YAML manifest files, and they are created in a Kubernetes cluster using the kubectl command line tool. The first Kubernetes object that we will look at is called a pod. And a pod is defined as the smallest deployable units of computing that you can create and manage in Kubernetes. Pods define how one or more containers are run. What we can see from this definition is that Kubernetes builds on the concepts we explored in Docker. Specifically, that Kubernetes is responsible for creating containers based on images and combining one or more of them into a pod. Here we have an example of a YAML manifest file describing a Kubernetes pod. The high-level structure of these YAML files is shared between all Kubernetes resources, including the fields API version, kind, metadata, and spec. The API version and kind fields describe the type of object that we want to create in Kubernetes. The metadata property describes the object, and in this case defines the name of the pod that we are creating. The spec then defines the properties of the object that we are creating. A pod defines one or more containers, which are defined under the containers property. And here we define a single container with the name of web app, referencing the Octupos underwater app sample image, and exposing the port 80. The apply command creates the Kubernetes object defined in our YAML file in the Kubernetes cluster. We need to pass the .f argument to indicate that we're referring to a file, and we then pass in the name of the manifest file that defines the Kubernetes object that we want to create. kubectl reports that the pod object has been successfully created, And we can confirm this by using the get command to list the pods that are represented in the Kubernetes cluster. From here we can see that the pod has been created and is running successfully. One of the benefits of Kubernetes is the ability to run pods across multiple nodes. If the nodes are deployed on separate virtual machines or physical machines, this provides a degree of high availability because if any one node goes down, the pods will still be running on some of the remaining nodes. To achieve high availability though, we need to run multiple instances of pods. And to do that we use a replica set. A replica set is defined as an object whose purpose is to maintain a stable set of replica pods running at any given time. Here we have a sample YAML manifest file defining a replica set. This replica set will deploy 3 pods containing the sample application that we created in the previous video. As before, we use the kubectl command line tool to create this object in the Kubernetes cluster. kubectl has reported that the replica set has been created, and we can confirm that with another get command. Here we can see that 3 instances of the web app pod have been created out of the 3 that we requested. We can then see the individual pods that were created by the replica set with another get command. Here we can see the pod called Underwater, which we created in the previous video, and below it 3 new pods starting with the prefix web app that are managed by the replica set. Deployments are another Kubernetes object that allow you to create multiple instances of pods. A deployment is defined as an object that provides declarative updates for pods and replica sets. What this means is that deployments add a number of features that allow you to control how updates are propagated through your cluster when you update a deployment resource. Deployments allow you to use the rollout deployment strategy, which progressively replaces pods with newer versions. This reduces downtime by ensuring that there are always pods available during an update. Deployments also have the recreate strategy, where all previous pods are deleted before new versions are deployed. Deployments also allow you to roll back to previous versions of a deployment. The deployment YAML manifest files are very similar to replica sets. In practice, very few people seem to deploy replica sets these days, as deployments offer all the functionality of replica sets, while also providing the ability to control how new versions of a deployment are rolled out. As before, we create deployment resources using the kubectl command line tool. A deployment actually creates a replica set in the background, and we can confirm this using the get command. The replica set shown here is created by the deployment resource. And as before, the replica set creates the requested pods. The 3 pods here are created by the replica set, which is in turn created by the deployment object. In this section we'll look at the service resource, which allows us to expose pods to external network traffic. A service is defined as an abstract way to expose an application running a set of pods as a network service. The important phrase in this definition is abstract. This means that network clients that call the service don't need to have any understanding of the pods that the service directs traffic to. You could have 1 pod or 100, and the network client will make the same request to the service regardless. To demonstrate a service, we'll create a service of the type load balancer. This is one of the 3 different types of services provided by Kubernetes. In order to enable load balancers on our kind development cluster, we need to follow the instructions in the kind documentation shown here. One thing to note is that these instructions only work for Linux, as noted in this highlight at the top of the documentation. Enabling load balancers in kind involves copying and pasting a number of commands. So copy and paste this command here. One thing to note is that the file that we pass into kubectl in this case is actually a URL. This is a neat feature of kubectl that allows us to apply files hosted on a web server. We'll next apply the the second manifest file. And we then run this kubectl watch command to wait for the pods created by the previous manifests to be in a running state. And as we can see, those pods are running, so everything is good. The final step involves determining the network addresses that are available for load balancers. And we can do that running this command here. One thing to note is that the documentation suggests a network range is provided by Docker in this range here, which is 172.19. On my system, the address is slightly different. It's 172.18. All this means is that we have to adjust some of the values in the sample manifest file provided here to reflect the address range exposed by my local system. Here I have a copy of the sample manifest YAML, and I have updated the address range here to reflect the addresses available on my local system. We then apply this config file. And at this point we now have the ability to deploy load balancer services. Here's the YAML that represents the load balancer service. You'll note the type of the service is set to load balancer, that it directs traffic to pods whose labels match the value of web app and the key of app, and that we expose traffic on port 80 and redirect it to port 80 on the pods. All that remains now is to apply that service YAML file. Once the service has been created, we can get the IP address that it exposes with a get command. Here we can see that the pods are now exposed on the IP address shown here. We can then open the sample application by pasting this address into a web browser. And here's our sample application up and running. Now that we've seen the basic concepts required to deploy a sample application to a Kubernetes cluster, we can move on to Octupos Deploy, where we will automate the deployment of applications into Kubernetes. There are a number of concepts and resources that we need to set up in a Octupos instance before we can start deployments though. In this section we'll look at how we configure an Octupos instance to perform Kubernetes deployments. The first aspect of the Octupos instance that we'll configure are the environments. We have a definition here of environments, which are described as how you organize your deployment targets, whether on-premises servers or cloud services, into groups that represent the different stages of your deployment pipeline. For instance, development, test, and production. What this means in practice is that you will have copies of your infrastructure and applications separated into multiple environments. The environments are as identical as practical in order to ensure that deployments to one environment can be repeated in a subsequent environment. Environments are typically used to gain an increasing amount of confidence that the applications and infrastructure you are deploying work as expected before they reach their final end users. Here I have a hosted instance of Octupos in a brand new space, and this is where we will create the first environments. To do so, you click the Infrastructure tab, the Environments link, and then the Add Environment button. We'll add two environments, one called Development, which I can pre-populate by clicking this link here. If I return back to the environments and click the Add Environment button again, I will then add the production environment. These environments are then placed in what's known as the default lifecycle. So if we click the Library tab and go to the Lifecycles link, we will see that there is a default lifecycle that contains the environments that we create in the same order that we created them. Next we need to create a feed. So a feed exposes version packages hosted by the Octopus server or an external repository. In our case, because we're deploying Docker images, the external repository will actually be the Docker repository. And in this case, specifically the Docker Hub repository. To create a feed, we go to the Library tab, click the external feeds link, and then click add a feed. We will select a Docker container registry as the feed type. We'll call it Docker Hub. And by default, the URL is already pre-configured to point to the Docker Hub feed URL. What we need to do here is click Save. In order to connect our hosted Octopus instance to the cluster hosted on our local machine, we need to install what's called a worker. So a worker is defined as machines that can execute tasks that don't need to be run on the Octopus server or individual deployment targets. We'll expand on this definition to say that workers provide a way to execute tasks close to the service or virtual machine that the tasks eventually execute against. In our case, we'll create a worker on our local machine to connect back to the hosted Octopus instance. And this will allow a hosted Octopus instance to reach inside of our local development workstation to connect to the development Kubernetes cluster. To install the Octopus Tentacle on Ubuntu 22.04, we first need to install the libssl 1.1 package. This package is not available in the default package repository, so we do need to manually install it. I'll use the instructions here from the Ask Ubuntu site. The first step is to download the package with this command here. We then install the package with this command. Once the dependencies have been installed, we can then set up the third-party repository holding the Octopus Tentacle software with these commands here. And we then install the Tentacle software with this command here. Once the Tentacle is installed, we can configure it using the script located at the end of the output message shown here. We'll accept the default name for the Tentacle instance. We'll create a polling tentacle. A polling tentacle makes an outbound connection from the instance that it's installed on, and this means that the virtual machine or workstation that the tentacle is installed on does not need to have a static hostname or IP address. We'll accept the default location for the log files as well as the application files. We then need to paste the address of the hosted instance, which in this case is 10pillars.octopus.app. We will use an API key to establish authentication between the Tentacle and the Octopus instance. To create an API key, you first go to your profile page and then click the My API Keys link. Click the new API key button. Give the API key a name. And you can optionally set the API key to expire after a certain period of time. The API key can be copied to the clipboard and then pasted into the terminal. We're going to set up a worker, and we will register this worker in the space called K&S training. The default name here was fine. So we do need to set up a worker pool in order to place the worker in. To do that, we go to the infrastructure tab, go to worker pools, and then we will create a new worker pool with this add worker pool button here. We'll call this worker pool laptop, and it is of type static. Click the save button. We'll then type that worker pool name back into the terminal. Click the enter key to configure the Tentacle instance. And at this point, the Tentacle is now connected to our Octopus instance. We can view that by going to Workers, selecting the new worker instance, and performing a manual connectivity check. Actually, we can see that an automatic one has just passed in the last few seconds. So if we return back here, we will see that the status is now green and our worker has connected successfully. Before we can configure the Kubernetes target, we first need to import the certificate that the kind development cluster uses for authentication. The details of the certificate are found in the Kubernetes config file shown here. The two fields shown here, client certificate data and client key data, are base64 encoded strings that contain the data we need to create our authentication certificate. To decode these strings, the easiest way is to copy and paste the base64 encoded string, use the echo command to echo it back out, and then pass that to the base64 command with the -d argument to decode the string. This text here is then the decoded copy of the original string. We'll paste that into a text document and then repeat the process for the client key data. The combination of the certificate and the private key allow us to create a certificate that we can use to authenticate with the kind cluster. So we copy those two blocks of text, return to Octupos, where we can find the certificates page under the library tab, and we click the certificates link, and then we can click the add certificate button. We'll call this certificate kind development cluster, and we can paste that text in to create the new certificate. Once we have imported the certificate, we can then create the Kubernetes target. So to do that, you go to the infrastructure tab, click deployment targets, click add deployment target, select the Kubernetes cluster, and then click the add button. We will call this development kind cluster. The target will belong to the development environment, and it will have the role of Kubernetes. You can think of roles as being like tags that are used when selecting a target for a deployment step, which we'll see later. The authentication is performed by our client certificate. We select the certificate that we created earlier. We then need the cluster URL, and that comes from the Kubernetes configuration file. Scroll up here, we can see the server property defines the URL that the kind cluster can be accessed on. We will skip TLS verification for now. We will use the default Kubernetes namespace, and we will connect to the cluster through the workers in the laptop worker pool. Once the target is saved, we can go to the connectivity tab. And as we can see that a health check was performed in the last few seconds. So if we return back to the settings tab, we can see that our cluster is online and healthy. At this point, we have everything we need to perform a Kubernetes deployment via Octupos. So the next step is to create a deployment project that will deploy the Kubernetes deployment resources and service that we created manually through the terminal earlier. To do that, we'll click the Projects tab, click the Add Project button, and we will call this Deploy Underwater App. We then define the deployment process and add a deployment step. The step we'll be using is called Deploy Kubernetes Containers. Which is this one here. This step will be run on the same laptop worker pool that we used to connect to the Kubernetes cluster earlier. The deployments will take place on targets with the role of Kubernetes. And we can then either edit the raw YAML of the deployment resource, or we can go through the user interface and build up all the individual elements that make up the deployment. Because we already have the deployment YAML, it is easier for us to simply copy and paste the YAML into Octupos. So we'll copy the YAML that we deployed earlier via the console and paste it into the YAML text box presented here. We also want to expose this deployment via a service, and that is done by scrolling down to the service section here. Again, we can set this all up by clicking through the individual options exposed by the user interface, but we can also copy and paste existing YAML, which we will do here. One thing we will do is use a different namespace. This will allow the deployment made from Octupos to be separated from the deployments that we performed on the terminal. So we have a definition here that says namespaces provide a mechanism for isolating groups of resources within a single cluster. Namespaces are often used to isolate separate applications and can sometimes be used to isolate different environments within a cluster as well. So I will call this namespace underwater. Let's click save. Once the step is saved, we can create a release. Octupos will query the Docker registry for the versions of the image that are available. And in this case, we have the latest tag being used as the latest version available. Then click save. And we proceed to deploy this to the development environment. We then click deploy to initiate the deployment. Here we can see that the deployment has succeeded. What we now need to do is find the IP address of the service that was created by the deployment performed by Octupos. Previously, we extracted that IP address by running kubectl from the terminal directly. To run those same commands through Octupos, what we will do is create a runbook. So if I click the Operations tab here, click Go to Runbooks, and then click the Add Runbook button, we create a runbook called Get Services. And in the runbook, we will add a step. And that step will run a kubectl command for us. So I click Add on this step here. This has to be run through the laptop worker pool. It'll be run on the targets with the role of Kubernetes. We'll be running a bash script, and then we will say kubectl get services, and we'll use the all namespaces option to ensure that we pick up the services that were created in the underwater namespace that was created previously with the deployment. Click the save button, and then click the run button. We will run this step in the development environment. Click the run button. If we look at the task log, we will be able to see the output of the command. And here we can see the two load balancers. This was the one we created manually with kubectl commands executed directly in the terminal. And this one here in the underwater namespace is the service that was created by the Octupos deployment. So we can, again, copy that IP address, paste it into our browser, and here's our sample application. Now that we've demonstrated automated deployments through Octupos to Kubernetes, it's time to set up a second production cluster so we can simulate the deployment of an application across multiple environments. We need to create a second Kubernetes cluster to represent our production infrastructure. To do this, we will run the kind command to create a second cluster, but this time passing in a name. Naming the clusters allows us to run two development clusters on the same workstation. To create the cluster, we use the kind create cluster command. And this time we pass in a name of production. We then need to extract the certificate used to authenticate with the new cluster. As before, we find those details in the Kubernetes config file. The configuration file now contains the details of two clusters. The first is the cluster with the default name of kind, and the second is the cluster with the name of production. If we scroll down to the bottom, we can see the certificate details for the production cluster. And as before, we need to decode the base64 encoded strings here to build up the certificate. So to do that, we echo the encoded string out, pipe it to the base64 command, and decode it with the -d argument. Copy and paste that into a text document, and repeat the process for the client key data string. We copy and paste the resulting text into a certificate, which we find under library, certificates, and we will add a second certificate. We'll call this the kind production cluster. As before, we paste the contents in to create the new certificate. We then need to add the production cluster as a target. So we do that by clicking infrastructure, deployment targets, add a deployment target, Kubernetes cluster, and adding the target. Call this kind production cluster. This belongs in the production environment. It will have the same role as the development cluster. It will be authenticated via the new certificate we just created. And we get the URL for the production cluster from the Kubernetes config file. We will skip TLS verification here. Again, we'll use the default namespace, and we connect to this using the workers in the laptop worker pool. Go to the connectivity tab, we can run a health check. And that health check has completed successfully, so all the configuration is valid and working. We then need to enable the production cluster to host load balancer services. So again, we rerun the instructions available in the load balancer documentation for kind, but this time against the production cluster. To interact with the production cluster, we need to change the context that kubectl uses when issuing commands. And to do that, we run the kubectl config use context command. This time we pass in the name of the production cluster. At this point, we can rerun the kubectl commands listed in the kind documentation. All that's left now is to progress the deployment from the development environment to the production environment. We do that by clicking the deploy button in the production environment, and then clicking the deploy button again to initiate the deployment. Once the deployment has succeeded, we can rerun the get services runbook, but this time run it in the production environment. Task log will show the IP address of the service that has been deployed to the production cluster. We can paste that into a browser, and as we can see, the application has now been deployed to the production environment. In this section, we will explore the deployment strategies exposed by the deployment resource in Kubernetes. To do this, we will install a dashboard to help us visualize deployments as they happen. Installing third-party applications into a Kubernetes cluster is often done by a package manager called Helm. Helm is defined here as a tool that helps you manage Kubernetes applications. Helm charts help you define, install, and upgrade even the most complex Kubernetes application. You can think of Helm as a package manager for Kubernetes in much the same way as package managers like Chocolatey, Homebrew, apt, and Yum install applications onto their respective operating systems. Most of the tools that you will install into a Kubernetes cluster to help you manage and monitor it will have the option of installing them via a Helm chart. The Helm website includes documentation for installing the Helm command line tooling, and here we have instructions for installing Helm through package managers for the major operating systems. So we have Homebrew for Mac, Chocolatey for Windows, and using the apt package manager for operating systems like Debian and Ubuntu. And these are the instructions that we will use for our local workstation here. So to install Helm, we simply need to copy and paste these instructions here into a terminal. Once Helm is installed, it can be executed with the Helm command line tool. We will install the Kubernetes dashboard using Octupos, and to do that we need to add the Helm chart repository as an external feed. To do this, we go to the Library tab, External Feeds, Add Feed, and select the Helm feed as the feed type. The dashboard that we will be installing is called Kubernetes View. We can see here the instructions provided for installing the dashboard via the terminal. What we can see from these instructions are that the repo that hold the dashboard charts are found in this address here. This is the URL that we need to copy into our Octupos feed. We can then save our changes to create the new feed in Octupos. If we return to the instructions to install the feed, we can see that the name of the chart is described here, Kubernetes View. We can verify our feed works by searching for this chart in the feed in Octupos. We click the test button, we click the package name, click search. As we can see, the Helm chart has been discovered, which means our external feed is configured correctly. The next step is to create a project that we can use to deploy the dashboard to our Kubernetes cluster. So to do that, we go to the Projects tab, we click Add Project, and here we will call the project Kubernetes View. We will define the deployment process. We'll add a step. And we will use the Helm chart deployment step included with Octupos, which is this one here, upgrade a Helm chart. This step will run on the laptop worker pool. It will run on targets with the role of Kubernetes. We then select the chart that we need to download from the external feed, which in this case is this chart here, Kubernetes view. We need to give the Helm release a name, and we will use the same release name as the package ID that we used earlier. And finally, we need to set a value that configures the service to be of type load balancer. This will give us an IP address that we can use to point our browser to in order to open the dashboard. There are many ways of defining values passed to a Helm chart, and here we will use the explicit key values option. So click the add key value button here. The key will be of type service.main.type. This defines the type of the load balancer exposed by the chart, and we need to set that to load balancer. Click the save button. Scroll up and click create release. You will notice that the latest version of the chart has been selected by default. Click save. Click deploy to development. Click the deploy button. And Octupos will proceed to deploy the Helm chart to our Kubernetes cluster. If we view the task log, we can see the output of the Helm chart. And what it tells us is that we can extract the IP address of the load balancer by using this command here. We can also rerun the runbook that we created previously to view the IP address. So to do that, return to the dashboard, go to our underwater app project, click runbooks, run the get services runbook, and run it in the development environment. In the task log, we can then see the kubeops view service has an external IP shown here. If we copy that and paste it into our browser at port 8080, we will open the dashboard. Kubeops view bills itself as a read-only dashboard for Kubernetes. There are far more capable dashboards if you want to use a web-based interface to manage a Kubernetes cluster. The nice thing about Kubeops View is that it gives you a real-time and animated view of your Kubernetes resources. What we can see here is the large square on the outside represents the cluster, the smaller square inside represents a node, and the green squares in the middle represent pods. This live view of the Kubernetes resources allows us to observe the behavior of different rollout strategies. To see this in action, we'll update the step that deploys the underwater app sample application. What you'll note is that the deployment strategy has been set to the rolling update strategy by default. And to simulate an update of the pods that we are deploying, we'll add a dummy environment variable. To do that, we go down to the containers, we click the container in the pod, we then scroll down to the environment variables section, and we add just a sample environment variable. This environment variable won't be used for anything, but Kubernetes will see the change as a reason to update the pods in the cluster. We save those changes. Scroll to the top, create a release. Save the release. Deploy the release to the development environment, and then initiate the deployment. What you'll notice as the pods are updated, one pod will be added as one pod is removed. So here's a new pod being added, and then a pod is removed, another pod is added, a pod is removed, and another pod is added. And then the final pod is removed. What we can see from this process is that a rolling update incrementally updates the pods in a cluster. This minimizes downtime by ensuring that there is always a pod available to handle requests while the other pods are being updated. Let's now observe what happens when we change the deployment strategy to recreate. So to do that, we'll go back to the deployment process, click the step, expand the deployment strategy section, and set the option to recreate. To force Kubernetes to redeploy the pods, we will change that environment variable to trigger an update. So again, we go back down to containers, click the container, scroll down to the environment variables, and we will just modify this environment variable to force an update. We'll save those changes, create a release, click the Save button, deploy this release to development, and initiate the deployment. Watch now how the pods are updated with the new recreate strategy. Notice that all 3 pods were deleted, and the 3 new pods were installed in their place. The recreate strategy first removes all existing pods, and once they are deleted, recreates them with the new version. This strategy does introduce some downtime, as there is a period of time between the pods being deleted and recreated that the application won't be available. But it ensures that the old versions of the pod and the new versions of the pod are not running at the same time. The final deployment strategy is called the blue-green strategy. And we can enable that by selecting it in the deployments strategy section here. Blue-green deployments are not native to Kubernetes, they are orchestrated by Octupos. The benefit of the blue-green strategy is that it will completely deploy a new set of pods before removing the previous ones. This allows the new pods to be completely deployed and tested with any health checks before switching traffic over. Like the rolling deployment, it minimizes downtime by ensuring that there is always a set of pods available to take traffic. Unlike the rolling deployment though, traffic is either directed to the old pods or the new pods, but not both at the same time. To observe the blue-green deployment, we will select blue-green deployments here, click the Save button, create a release, save the release, deploy it to the development environment, and then initiate the deployment. What we'll see in the dashboard is 3 new pods created, and then the old pods cleaned up. So there are the 3 new pods. We wait until they're completely deployed and the old pods are then removed. The sample applications we've deployed so far have been very simple in that they're totally self-contained and don't include any external configuration. Most production applications deployed to a Kubernetes cluster are not this simple though, and they frequently require external configuration in order to connect to external resources like databases or other services deployed to the Kubernetes cluster. Kubernetes provides 2 resources that are designed to host configuration values frequently used by applications. The first is a config map, and the second is called a secret. A config map is defined as an API object used to store non-confidential data in key-value pairs. Pods can consume config maps as environment variables, command line arguments, or configuration files in a volume. There's 2 key parts to this definition that are worth focusing on. First is that a config map is used to store non-confidential data, and the second is that the data is stored as key-value pairs. The definition of a secret is an object that contains a small amount of sensitive data, such as passwords, a token, or a key. Such information might otherwise be put in a pod specification or a container image. So what we can see about a secret is that it's designed to extract sensitive information out from pod definitions where they may otherwise be viewed in plain text or otherwise unprotected. It's also worth noting here that a secret also stores data as key value pairs. Frequently though, that data is something like a certificate, which is a binary file. So as we'll see, the data stored in a secret is base64 encoded to allow such binary data to be copied and pasted relatively easily in text documents. Before we dive into a demo, it's important to understand one of the consequences of using an external resource like a config map or a secret to configure pods. As we saw in previous videos, the deployment strategies used by deployment resources include strategies like rolling deployments. And in this scenario, the previous version of a pod is run side by side with the new version of the pod, and the deployment strategy replaces the old versions of the pod incrementally with new versions until only the new versions of the pod remain. This has some interesting implications when config maps are used to configure pods. So what we can see here is a diagram showing the initial state of a deployment, and we have 3 pods all at version 1, configured with a config map also containing version 1 data. During a rolling deployment, what may happen is that the second version of a pod is rolled out side by side with the first version. And in this case, version 2 of the pod is still accessing version 1 of the config map. Eventually, version 2 of the pods replace all version 1, and we're left with this, where we only have version 2 pods, but still connected to version 1 of the config map. And then as a second step in the deployment, we may then update the version of the config map to reflect the data that is responsible for serving version 2 pods. So if we go back to this intermediate step where the version 2 pods are incrementally replacing version 1 pods, what you'll notice is that there's no point here where we can have a version of a config map that is tied to a specific version of a pod. Either we retain the old version of the config map, which is version 1 in this case, used to support version 1 of the pod, or before we initiate the deployment we update the config map to version 2, in which case at this point version 1 pods would be pointing to a version 2 of the config map. So when a single shared config map is used to configure a single deployment, we can quite often run into situations where the version of the data stored in the config map either doesn't suit the previous versions of the pod, version 1 in this diagram, or doesn't suit the version 2 of the pod. And this conflict can lead to some subtle and very hard to debug issues during your deployment process. A better way to organize your deployments is to ensure that the pods all point to their own specific version of a config map. So here we have an example where the version 1 of pods is pointing to their own version 1 of the config map, and the version 2 of pods are all pointing to their own version 2 of a config map. What we have here is the intermediate step during a rolling deployment where version 1 pods and version 2 pods are running side by side. But at this point, because they each point to their own specific version of a config map, there is no conflict. We then proceed to the end of the rolling deployment where all version 1 pods have been replaced and only the version 2 pods remain, and again they still continue to point to the version 2 of their config map. So this scenario is important because none of the documentation I've ever read highlights this potential conflict when performing things like rolling deployments. It's very easy to find examples on how to configure a pod or pods created by a deployment with a config map or a secret. But they always assume that there is a single secret that can be used across all versions of the pod, regardless of deployment strategies like rolling deployments where previous versions of the pod are run side by side with the new version. Having pod-specific configuration in the form of deployment-specific config maps or secrets is obviously a very important part of a deployment strategy though. And for this reason, the ability to create specific config maps and secrets with each deployment is tightly integrated into the deployment process orchestrated by Octupos. We'll see this in action in the demo where we deploy a sample application configured by a config map coming up in the next section. In this section, we'll demonstrate how to configure pods using external values stored in secrets and config maps. The example YAML here is for a secret, and as you can see, the key value pairs define a password for a database and a root password. The values here are base64 encoded. The values held by secrets are quite often relate to binary data such as certificates or other authentication tokens. And so base64 encoding them allows this binary data to be copied and pasted easily in text files. The type of this secret is set to opaque, and this means that this secret contains generic user values in terms of key value pairs. The Kubernetes documentation lists the types that are available for secrets, and as you can see from this table here, the types frequently refer to certificates or other authentication values. The second resource is a config map, and here we have created a JSON blob that is assigned to the key called config.json. We'll use this JSON blob as a file mount in a pod, and this will demonstrate the ability to configure pods by injecting custom files into the file system used by the container. To demonstrate configuring pods with secrets and config maps, we'll deploy a sample application that represents a very simple online bookstore. This application will have a backend service that persists its data in a MySQL database and a front-end web app that displays the bookstore in a web browser. We'll first start by deploying the MySQL database to the Kubernetes cluster. To do that, we'll create a new project group to hold our deployment. So to do that, we go to the Projects tab, we set Add Group, and we'll call this Octopub. We'll then create a new project that will deploy the MySQL database to Kubernetes. So to do that, we click Add Project. We'll call this MySQL database, and we then configure the deployment process. However, before we start adding steps to the deployment process, we do want to define a variable that will hold the secret representing the password used to access the database. So to do that, we go to the Variables tab and go to Project. Here we'll create a a variable called database.password. Set the type of this variable to sensitive, and then enter a value for the database password. We're free to choose any password that we like here, so I'm going to go ahead and select the automatically generated password created by my web browser. We click that Add to List button and then Save to save the changes. We then return to the deployment process. We will create a process, and we will use the deploy Kubernetes containers step to deploy our MySQL database. Okay, we'll call this step deploy MySQL. This has to be run on the worker contained on my laptop, and it will be done on behalf of the targets that have the Kubernetes role. Now, in this example, we'll actually go through and use the user interface to build up the deployment. Previously, we've copied and pasted raw YAML into this text box here, but the same process can also be applied through the user interface, and we'll do that here. So the deployment name will be called database. We will use the rolling update strategy here. Before we define any containers, we will create a secret resource to hold the sensitive credentials that are associated with the database we are deploying. So to do that, we need to enable the feature up here. We need to ensure that these are enabled. They are enabled by default, so we can see that this feature here enables a secret to be defined with the deployment, and this one here allows a config map to be defined. So if we scroll down to the section where we define the secret, which is here, we will create a secret called database, and in this we will define the key called password, and the value we will set to the secret that we defined in the variables earlier. The next step is to create a container to run the MySQL database and configure it with environment variables that are either non-sensitive, which will be things like usernames, or that are sensitive, that reference the value in the secret that we created here. if we go back to the containers section, we will add a container. We will call this MySQL. This will be configured with the MySQL image from Docker Hub. We need to expose port 3306, which is the default port used by MySQL. Give this port the name of database. And then we need to define a number of environment variables. So the first environment variable will be the username of the regular user that a client will use to connect to the database. And in this case, we'll call it product. We then need to define the name of the database that we want to have created for us. And again, we'll call this product. So these values are not sensitive and they can be safely stored in plain text as environment variables. The next two settings, though, are passwords associated with the database. And these are sensitive values, and so we need to define environment variables with the values sourced from the secret that we created earlier. So to do that, we use the secret environment variables section here. So we'll click add an individual environment variable from a secret. The name will be MySQL password. So this defines the password for that regular user, which in this case was called product. In this field, we need to define the name of the secret resource that we are consuming this secret from. The name of the resource that we created in the user interface previously was called database. But as we saw earlier, one of the opinions that is baked into this step is that resource is tightly bound to a deployment, and those include things like config maps and secrets, are created as unique resources with every deployment. Octupos achieves this by appending a unique value to the name of the secret with each deployment. So the suffix is a dash, and then the deployment ID, which we can find in the list of variables here, .id, so it's this one here. And then we use a filter to convert this to lowercase. This is important because names in Kubernetes can only be lowercase characters, whereas the deployment ID may include uppercase characters. So by including the filter to lowercase, we ensure that the end result is the lowercase version of this variable here. So the key is the key that we created in the secret, and in this case it was password. We need to create a second environment variable called MySQL root password. But again, we're just going to use the same password for both the regular user and the root user for our example here. So if we click OK, we can see then that we have created a container, and the summary of the container is shown in this tile here. Save these changes by clicking the Save button. One thing we may want to do here is actually deploy this to a new namespace. So I will just populate this here and call it Octopub. Just click Save again, and then we will initiate the deployment by going Create Release. We can see here that the latest version of the MySQL image has been automatically selected. Click Save to save those versions. We will deploy to the development environment and then initiate the deployment. So the deployment has succeeded. One trick we can use is to inspect the YAML that was deployed by Octupos by using the verbose logs in the task log. So I click the task log tab here, and under log level, I click verbose. What we can see, if we scroll down to the deployment step, is the verbose logs contain the YAML of the resources that were created. So here we can see that Octupos has created a secret and called it generic deployments 2565. So this name here, database, this was the value that we entered into the step. And this dash deployments 2565 is the suffix that is automatically appended to resources like secrets and config maps in order to tightly bind them to a particular deployment. This suffix here is also why we needed to append the value of the deployment ID and then convert it to lowercase when we were referencing the secret as an environment variable. So if we scroll down to the YAML of the deployment object, we can see that the secret that is created by this particular deployment is what we are referencing for the pods created by the Kubernetes deployment resource. So it's important to note that this value here, this name here, was automatically generated by Octupos, and that is an opinion that is baked into the step. Every secret or config map created as part of that deploy Kubernetes containers step will always have this suffix, and this suffix will always be unique, generally with an incrementing value here for every deployment processed by Octupos. This value here is what we needed to create in the step to reference that secret. And so this is why we needed to append that variable octopus.deployment.id and cast to lowercase characters. So to demonstrate the fact that secret resources are in fact specific to each deployment processed by Octupos, we will create a new deployment now and redeploy the MySQL container. So if we go back to the project here, and then we'll go create release. Save that release. Deploy it to the development environment, and then click the deploy button. So what we expect to happen here is that the ID appended to the end of the secret resource has changed between the first deployment and the second deployment. So if we return to the task log and look at the verbose logs, we can indeed see, if we show all, that the secret created by Octupos, which is shown down here, includes a new unique suffix. So in this case, the ID or the number here has been incremented by 1 to 2566. That unique secret is then referenced by our deployment resource, which you can see here, again, referencing that incremented number of 2566. Importantly though, once the deployment has succeeded and the previous versions of the pods have all been replaced, Octupos will then go through and delete any unused resources, like previously deployed secrets and config maps. So here we can see that the secret with the suffix 2565, which was the previously used secret that was associated with the previous deployment, is now cleaned up for you. And so this means that when you use these tightly bound resources in your deployment, Octupos will take care of cleaning up any unused resources once the deployment has completed successfully. Now that the database has been deployed, we need to deploy the backend service that persists its data in the MySQL database. So to do that, we'll add a new project. We'll call the project product service. And as before, we need to define the password used to access the database. So to do that, we go into variables, project. We add a variable called database.password, and then paste the value of the secret that we use to configure the MySQL database. Add that to the list, save the changes, and return to the deployment process. As before, we will deploy our container with the deploy Kubernetes containers step. Okay, so we'll call this one deploy product service. As before, we will create a secret resource to hold the database passwords, which is done here. Secret name will be called database, and the values will be called password. And that will be set to the value of the secret variable that we defined earlier. We return up here. We'll need to give the deployment a name, call this product, and we will add a container. Call this product. The image here is called product service MySQL, and it comes from the Octupos samples organization under Docker Hub. We need to expose port 8083. Call this web. We then need to set two regular environment variables. The first one is called database username, and this is the same name that was assigned to the MySQL underscore user environment variable where we configured the database. And we then need to set the host name of the database. And in this case, we're going to set it to DB. What we'll see shortly is we need to expose the database as a service called DB in order for our backend service, our backend application code to be able to access the database via the network. The final value is the password that we use to connect to the database, and this is what has been saved in the secret. So the environment variable name is called database password, secret name again is called database, and then the deployment ID as lowercase, and the key was password. Let's click OK. We need to be able to access this backend service through a web browser, and to do that we need to expose it as a load balancer service. So if we scroll down here to the service type, we'll create a load balancer of type, a service of type load balancer, call this product as well. And then we will expose the port, we'll expose port 80, which is the standard HTTP port, and we will link that to port 8083, which is the port exposed by the pod. So we'll save that. I need to select a role and the worker pool. So I need to select laptop here, and then on behalf of Kubernetes. Let's try again. And that value has been saved. Now, before we perform this deployment, we do need to go back to the deployment of the database and expose it through a service. So we'll go back to the Projects tab here, go to MySQL, go to the deployment process, click the Deploy MySQL step, and we'll scroll down and create a service, which is here. Service will have to have that same name as the database hostname environment variable that we set in the product service, which was just called DB. We'll set the service type to cluster IP. We haven't used this service type previously simply because it's been easier to expose everything with a public hostname or IP address that we can point our browser at. But in the case of a database, there's no need for anyone external to the cluster to access it. And what this means is that if we exposed it as a load balancer service, we'd actually be introducing a potential vector through which people could attack our deployments. So because it's not necessary to publicly expose our database, we'll use the default value of cluster IP. And a cluster IP assigns a hostname or an IP address that is only accessible to other pods running in the same cluster. And so in this case, the MySQL database will be exposed on the hostname called DB, and this will allow our product's backend service to connect to the database. So I'll click Save on there. Oh, I forgot to add some ports. We need to add the port. We're also exposing port 3306, and that will be linked to the same port inside the pod. So click Save there. And we will need to redeploy the MySQL database for it to create the service resource. The deployment has completed successfully, and if we look at the task logs, we will be able to see that the service called DB was successfully created. So if I just return to the projects for a minute and go back to the product service, I believe I missed a step. So if I go to the process, I think I have to set the namespace that the product service is deployed into. Scroll down here. Yeah, this does need to be set to Octopub. So the backend service and the database will be located in the same namespace. We can now create a release of the product service. And that deployment has now been initiated. Right, the deployment of our product service has completed. If we go to the task log, we can see that it has created a secret with the database credentials. We can see that the deployment product has rolled out successfully, and it has been exposed by a service, also called product. The final step, again, is to find the hostname or IP address of the load balancer service, and to do that we will use a runbook. So if we return to the operations tab and go to runbooks, click add a runbook, we'll call this get services. We will define a runbook process and add the step called inspect Kubernetes resources. This needs to be run on the laptop on behalf of targets with the Kubernetes role. We're going to look at resources of type service. Get is fine here. We'll limit it to the service called product, just so we don't return the details of all of them. And we need to set the namespace to Octopub. Save that, run the step, and run this in the development environment. Okay, so this runbook step actually failed, and if we look at the task logs, we can see that the error is because we're trying to run a PowerShell script on a Linux laptop. PowerShell is a cross-platform shell that works across Windows, Linux, and Mac. And what you'll find is a lot of the community step templates that we've used, and in this case we used that Kubernetes inspect resource step template. They're all built on PowerShell. The easiest way to fix this is to install PowerShell Core on your Linux workstation. So these instructions here are provided by Microsoft for installing PowerShell on Ubuntu. It's just a case of copying and pasting the commands into the terminal. Once PowerShell is installed, it can be run with the pwsh command. This enters into a PowerShell session. You'll notice that pwsh command is also the command that Octupos complained was not available. So now that we've installed PowerShell on our Linux workstation, we can rerun the step, and the step should work correctly. So this time the step completed successfully, and if we look at the task log, we will be able to see the external IP address of our backend product service, which is this one here. We go to here and export the list of products exposed by the API. We can see we return a JSON blob that is the result of calling that product service. And so this tells us that the product service is working correctly and that it has pre-populated the MySQL database with a number of sample books or blog posts. The final step is to deploy the front-end web app that is used to consume the API that we deployed through the product service. And so to do that, we will add a third project here called front-end web app. Our front-end web app doesn't need to consume any secrets, so we don't need to define any variables at this point. So we'll just jump straight ahead and define the deployment process. As before, we will deploy using the Kubernetes containers step. We'll call this step deploy front end. This needs to work on the laptop worker pool on behalf of targets with the Kubernetes role. We'll call this one front end. So one thing we do need to configure in this front end web application is a configuration file. This configuration file is a JSON blob that we will use to define the host names, paths to the external services. So in this case, we need to define the path to the product service, which is this IP address here. So to do that, we'll go down to the section where we define config maps. We'll call this config map, let's call it front end as well. It will have an item called config.json. And the value of this file will be a blob of JSON that we use to configure the front end application. And so that is, if we look here, that is this blob of JSON here. One thing we will need to do is replace these localhost host names with the IP address of our product service. So I'll copy and paste the IP address here, return here and replace localhost with that IP address, as well as the health check endpoint. So I copy the JSON blob here and paste it as the value here. Then that defines the contents of a file that we want to inject into our container to override the default values that would otherwise be hard-coded in the Docker image. We then need to define a volume that references the config map we created earlier. So to do this, we click the Add Volume button. The volume type is config map. Again, we'll just call this front end. And one of the conveniences of this step is that we get to reference the config map created as part of this step. And so this is really just a shorthand for saying, for defining the name of that config map resource and then applying the deployment ID to lowercase. So if we go deployment.id and say to lower, this value here is the equivalent of simply selecting this option here. And so this is far more convenient, and we'll simply do that. The key is the key that was assigned to the config map, and that is called config.json. This key also happens to be the name of the file that we want to inject into the container. So we repeat that as the path, config.json. Now that we have a volume that allows us to mount files inside our container from a config map, we can go ahead and create the container itself. So we'll call this container front end. The image is another one from the Octupos samples organization in Docker Hub. We'll expose ports 5000. And then we need to add a volume mount. So the name of the volume was front end. The mount path is going to be the full file name that we want to overwrite inside the container created by our Docker image. And so in this case, the full path is called workstation build and then config.json. In order to have Kubernetes inject just a single file into this path here, instead of treating this as a directory, we need to set the subpath to the name of the file as well. So this subpath here must match this file name here, and the combination of these two settings ensures that Kubernetes treats this file as a file and not a directory. So we click OK there. We also need to expose this front end through a load balancer service. So we'll do that here. Set the service name to front end. And we need to expose port 5000. But again, this is a simple HTTP port, so we'll expose it to the end user on port 80. So we'll click save. And then we'll go ahead and create a release. So we'll create release. Click the save button. Deploy to development, and then initiate the deployment. Actually, one thing I realized is that we didn't set the namespace of the front-end deployment. So this is going to attempt to deploy the front-end web application into the default namespace. That's easy fix though. We just go back to the deployment process, click the deployment step, return to the namespace field, and we need to set that to Octopub. Click the save button. We'll create a new release to reflect those changes. Click the save button, deploy to development, and then deploy. One thing you'll note is that Octopus can only process a single deployment to a single environment at one time. So the second deployment here will pause until the initial deployment succeeds. Okay, so our front-end web application has been deployed successfully. If we look down here, we can see a similar pattern with the config maps has been used for the naming convention as we did with the secrets. So this name here, front end, this was what we defined in the user interface, and this suffix is the unique ID that is appended by Octopus for each deployment. If we expand the verbose logs, we can see the volume section associated with the deployment has correctly identified the name of the config map that was created for this particular deployment. So this suffix here of deployments 2570 is the same as this suffix here that was appended to the name of the config map. And because of the convenience of that option where we were allowed to select the config map created as part of this step, we didn't need to manually append this name. Octopus was smart enough to be able to link those two up and keep those names in sync with each new deployment. As before, the final step with this deployment is to get the IP address of the service that we exposed as a load balancer, and again we'll do that as a runbook. So we'll add a runbook. We'll call this get service. We'll define the runbook process and add a step. We'll reuse that community step template called inspect Kubernetes resources, which is this one here. We'll call this get service. I'm going to run that on the laptop on behalf of targets with the role of Kubernetes. We want to get resources of type service, and we will limit it to the services called front end. We'll also need to make sure we change the space, the namespace. Save that. Run the runbook in the development environment. If we go to the task log, we will see the external IP address of our front-end web app, which is this one here. If we open this up in a new tab, we can see that we have successfully deployed the front-end app, and it has consumed the values of the books or blog posts that are exposed by our backend service here. So what's interesting here is that if we look at that config.json file directly, we can see how the text in the config map has been injected as a file called config.json, and this file is then consumed by the front-end app to determine the location of back-end services like the product endpoint here. So this is an example of using config maps to mount files into containers as a way of configuring services or applications.